Good morning, everyone. My name is Felienne Hermans. I'm assistant professor at Delft University of Technology, where I research spreadsheets. I promise it's the only time I mention it now. If you came here to see a talk about spreadsheets, this is not at all about it. This is not about my day job. If you're on Twitter, my Twitter handle is my first name, so I'm very easy to find. If you like things, if you see things you like or you don't like, feel free to mention me so I can read all about it later. So this one day at home, I was playing a board game with my boyfriend called Quarto. Who's heard of the game Quarto? Who knows how it works? Okay, only like 3 people. So it is a sort of a multi-dimensional 4 in a row. So with normal 4 in a row, you have black and white, and you need to get 4 of them in a row. With Quarto, the stones have 4 different properties. So they can be, as you see here, they can be white or black, they can be round or square, they can be short or long, or they can have a hole in the middle or not. So you have 4 different properties, and the objective of the game is to get 4 in a row for one of the 4 properties. So we were playing a few games after each other, and every time either I won or my boyfriend won. So we were wondering, would it be possible that this game end in a tie? Is that an opportunity? Is it something that could happen? So I don't know how normal people think, but I guess normal people would be like, I don't know, I don't care. But not, of course, at the end, but not, of course, in Nerdland. We were like, we can figure this out. Let's stop playing, let's bring out the laptop and solve this problem with some science. So the obvious thing you could do, of course, is brute force this. And because the board is pretty small, it's just 4 by 4, it's like this on your table. So you could think, now, how bad can it be? But if you think about it, it is actually quite bad, because in the first position on the board, of course, you have 16 options. You place 1, then you have 15 left, then you have 14 left. And it gets ugly pretty quickly. This is 16 faculty, which is that number, which I'm not even going to read, it's so big. And for every field assignment that you make, you have to do 160 checks, because there are 10 ways in which you can get 4 in a row. 4 like this, and then the 2 diagonals as well. So let's say you would do it on this machine, which has 4 cores and 2.6 gigahertz. You could do about 10 billion checks every second, but then it will still take you, any guesses? You can do the math very quickly, or just take a guess how long it will take. Oh, it's not that bad. Oh yeah, in seconds, so that is about 90 hours. So it's not very bad, but it will be sort of a ruining of our game nights if we have to wait 90 hours. So the problem is not really solved yet. Of course, you could say we will just wait 90 hours and then it's solved, but that would be boring and boring. So we're not going to do that. And so I figured, at one point I was in school where I had a course about automated reasoning that taught me a few tools that I could potentially use to attack this problem. And specifically this course was about SAT solving. So the idea that I then had was to transform the problem of Quarto into an SAT problem, solve that, and then get the answer. And that might sound a little bit abstract to you, so let me diagram it out for you. Instead of directly going from the problem to the solution, I will present my problem in an alternate representation, solve my problem in that alternate representation, and then transform it back. So maybe this is still a bit abstract. Let me give a simple example. So suppose I want to divide this number by 2, 78,974. That is a lot of work if I want to divide this by 2 manually. I could start at this side, so here I can take 2 2s there, etc., etc. Lots of steps, and eventually I will get the answer. But that is a lot of work. So what I could do, any suggestions, what representation would make it really easy to divide by 2? Binary, awesome. So suppose I would have this big number in a binary form. Now all of a sudden, dividing by 2 is really easy, because I would just bit shift. Yeah, so just scratch out the final 0, and then I have divided by 2. And then there's one more step I need to take, of course. If I want to have it in a normal form, in a decimal form, I will have to translate it back. So this is exactly what we're going to do in our quarto problem. Transform it into SAT, solve it there, and then transform it back. That's what we're going to do. Da-da-da. Are you ready? Let's science the shit out of this. So what is satisfiability? What is the binary representation that we're going to use? The idea of satisfiability is that you have a Boolean proposition, something like this, P or non-Q. And the idea is that we're going to find a truth assignment that satisfies this proposition. So for instance, for this very simple proposition, you could say P is true, and Q is false, so non-Q is then true. So this is super true. This is true or true, which is absolutely very much true. So there is some good news about this and some bad news. The good news is there are fantastic tools called SAT solvers that can do this very, very, very quickly. Every year there's an annual SAT solving competitions where people submit their SAT solvers and fight each other in different categories. So many people have worked on this and they are really, really smart. However, there's a downside. Oh yeah, sorry. This is how an SAT solver works. So you put a proposition in, and then it will tell you, this is satisfiable, yes or no. And typically, it will also then give you a truth assignment. So it won't just say yes, it will say yes in such and such way. But there's bad news as well. We haven't made our problem really simpler. It's still a hard problem. If you know what it means, the problem is NP hard. If you don't know what that means it's very, very, very hard. So the problem remains hard. However, there are very good tools that we can use to battle it. So the idea is to express our quarto problem using propositions. So what we could do is for every field, every square on the board, we represent it by a number of booleans. 4 booleans that represent the 4 properties that packs can have. So every field gets 4 booleans representing whether they are black or white, long or short, square or round, and flat and whole. So let's say this field is called 0, 3 because it's row 0 and column 3. Let's pretend that one is yellow. So every field gets 4 propositions. And if we have that, we have the setup of all the variables that we need. Because now we can express a tie. Because with the booleans, a tie looks like this. There is no row, column, or diagonal for which one of the 4 properties is the same. We can nicely express that for every property, all of the 4 properties P, for every combination S, so that is all rows, all columns, and the 2 diagonals, the stones in that combination do not all have the same value for that given property. Let's look at an example. Suppose we pick the first property, which is, I think it was length, but of course this is symmetrical. The first property on the first row, you would express it cannot be the case that for these 4 fields on the first row, they cannot all have the same properties. So we're almost done with our expression, but there's one more thing. The stones should all be different, because this is the way the game works. It would be cheating if I would go to a game shop and buy 5 quarto sets, and then with all the stones from all the sets would make a tie. That's not a real tie. So we want to limit ourselves to whatever is in the board, in the set. So all the stones should be different, and we can express that really nicely in Boolean language. No 2 stones may be the same. So I can say, for instance, field 0, 0, and 0, 1, they cannot be exactly the same. That means it cannot be the case that for every property, they have the exact same value. So we're done only with these 2 rules. There cannot be wins on a row or column, and all the stones have to be the same. We're done. But of course, I'm not going to type all this. I'm not going to type all the rules because all the properties, all the combination, that's a bit of a hassle. So I'll use a little program to generate the input. I don't always use SAT solvers, but when I do, I generate the input file. So now, maybe you could say the problem is solved, because I wrote this little C# program that initializes the board and then loops over the columns, the rows, and the diagonals, and also here adds a rule for these are not all the same. So I'm not going to go in the details of what happens within these methods, but this is sort of what happens. It generates rows for rules, columns, and not all the stones should be the same. So you could ask, why actually is this better? So now your problem is in an SAT form. You told us that there are these wonderful things called SAT solvers, but how is it actually better? What is happening on the inside that makes SAT solver so smart? So I'm going to go into a few tricks that explain, once we have it in an SAT form, how is it possible that they are so much quicker? How does an SAT solver work on the inside? So the basic thing, it's a bit of a sad news, but the basic thing what it does is it just tries all options. That is ultimately what happens. As I said, the problem is NP hard, so if you're unlucky, you will absolutely have to try all options. So that's the basic. Suppose we're solving P or Q and non-R. Well, we'll just make a truth table, 0, 0, 0. Ah, that's not it. And we repeat that until we get in a situation where it is satisfiable. That is basically what happens. But there are a few tricks that SAT solvers use to be more smart than just iterating over all options, because otherwise, ultimately, it would just be the brute force solution that we already know is very slow. So there is this little trick that you can use to reduce state space. If you have a formula of the following form, P or non-Q, and Q, this is equi-satisfiable, just as satisfiable as just satisfying P. This is a bit hard. So why is this happening? If you are solving something and Q, you might as well solve Q because both parts need to be true. And I did this talk before, and this was, I think, the part where I lost some people. So let's not look at the formulas, and let's pretend I'm Steve Tyler for a minute. I will help you understand how the proposition rules work by pretending I'm Steve Tyler. So I think he's known for always having outrageous demands if he gives a concert. So suppose I'm Steve Tyler, and I say, if I go into my hotel room, I want the following things: a Japanese newspaper, a bunny, blue M&Ms, one of these, and a bottle of whiskey. So a few things or a bottle of whiskey. So if I, Steve Tyler, me now, enter my hotel room and there's no bottle of whiskey, it doesn't even matter if the bunny is there or the blue M&Ms are there. If there need to be two things, both sides need to be there. So let's go back to the formula. This thing needs to be true, and that thing needs to be true. So I'm sure that that part needs to be true because it's by itself, and if that is false, it will never happen. Then if I know that this is true, then this part, the non-Q, will be false. Then at this side, the only way I can make this happen, because I already know that not Q is not going to happen, the only way I can make it happen is P, if P is true. So this is what we professionals call a proof by hand waving. It's called unit resolution, the trick, and it reduces state space, but you can actually prove this for the general case. So if you thought maybe I was cheating, or you thought I already know this, this is homework for the interested reader. If you like to figure this out, it is possible to prove this for the general case. So let's see how it works on an example, because maybe it's still a bit abstract. So here are a number of propositions, and as you can see, I wrote them down in quite a specific way. So these are all disjunctions, this or this or this or this, and then these are ands. This is a very easy way, and we will talk about why this is important later. So suppose we're solving this. The first thing, we don't know. We cannot do any unit resolution already, so there's nothing we can do. We just pick P is true. So we say, okay, P is true. It's just random. There's no choice there. So that means that this is false and this is true. So I make everything green, that's true, and everything red, that's false. Now, here we have a Steve Tyler situation. This is false, so this needs to be true, otherwise there is no saving of the situation. So we can deduce that non-S needs to be true, so S needs to be false. Otherwise, this is not going to happen, and this is one of the conjunctions. So that is a decision that we can make based on the information that we have. So we have to say S is false. Now, we're now again in a situation where unfortunately there's no free lunch. We cannot apply unit resolution anywhere because there's no situation where everything is red except for one. So we make another decision. Let's say we decide that Q is true. So this is true, that is false. And then again here, all of them are false. So this needs to be true because otherwise we will never have a good true assignment. So we make a decision, and then now we have an assignment where in all of the parts there's one green variable. So everything is true, everything is satisfied. And there were 4 variables, but we only needed to pick 2. We only decided 2, and the other ones were reduced using unit resolution. So you see, you can quickly prune the state space because you already know that certain things must be true, and that makes it a lot quicker than just trying all the possibilities. So in such a small situation that we have here, it is pretty easy to see where we can apply resolution. You just look at the clauses, and if everything except for one is red, then that is where we have to make a decision that that one needs to be green or true. But suppose we have a very, very long list of clauses, and this is something that's very commonly happening if you're transforming a normal problem from, let's say, the normal world into SAT, you're going to get lots and lots of rules. Already for our small quarto problem, we got lots of rules generated. So typically you'll have lots of rules, and then it gets very expensive to check every time, is there a situation in which we can do unit resolution? So again, you can only apply unit resolution if all of the variables except for one are red. If more than 2 are unassigned, are white in this situation, then there's no way we're going to apply unit resolution. And there's a trick called watches that keeps track of where are 2 unassigned variables per clause. So here I make the watches purple. As long as there are still 2 purples in our clause, we're not going to do unit resolution because they're still unassigned. So they're actually white, they're not red or green, they're unassigned. So we don't even have to look there as long as there are still 2 watches. So what happens with the watches? If a watched variable gets assigned, if we make him green or red, then we just move the watch. So suppose we're in this situation, we can do unit resolution here. So this is green. So we know the value of S now. So we just move the watches to any variable, it doesn't matter which one, because we just want to keep track of the fact, are there 2 purple places? Are there 2 spots that we can watch that will make it impossible for us to do unit resolution? So we just move it and we're done. And this means we only have to do unit resolution in this scenario where we're moving a watch. And here's the very smart thing about this. If we backtrack, so if we made a decision that turned out to be wrong, because we're still in the situation where we started with a decision, it could be the wrong one, so we end up at a dead end and we have to backtrack. If we backtrack, the watches do not have to move, and that makes it especially efficient because there will be backtracking going on. You'll see that if I run it later, and then the watches don't have to move. So let's make our list a little bit longer. Suppose somewhere here deep in our assignment, we had to pick S is true because there was some reason we picked S is true. Now we have a problem here, because here we have a conflict. This is false or false. That part is not going to happen, so the whole thing is not going to happen. That means we have to backtrack. Boo, conflict is what this is called. So we flip S. But as you can see, the watches can just stay in the same situation because the watches are watching unassigned variables, so they can stay in the same place. And this makes it especially very, very efficient. So we know how an SAT solver works now. I showed you what's inside, what makes it so quick. I showed you how to transform the problem to SAT. So you would say, now we're ready, right? We have our code, we know how it works, the problem is solved. However, not really, guys, we're not there yet. The problem is not solved. Because if you look at these clauses I generate, they don't really look, it doesn't look so easy to apply the unit resolution trick on them. They look very different. My clauses have equal signs in them, and they're not in this form where you only have disjunctions joined by a big conjunction. They are all over the place. They have knots here. SAT solvers are a little bit like Steve Tyler. They're a little bit picky about what they want and don't want to eat. So SAT solvers only work if you first transformed your input to this format, which is called a DMAX format. I'll show it to you later. But this is, isn't it outrageous? So you can quickly solve an NP hard problem, but you refuse to do a little bit of string manipulation. I think that's pretty diva. Like, no, 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 no. You have to give it to me in the correct format, or I won't do it. So we're still not done yet. We have to make sure that the rules that we generated are in the right format in order for an SAT solver to be able to eat it, to process it. So what I did was I wrote a tiny little library in F# that describes how terms look like. So what can I have? I can have variables with a string name. I can negate them, put a not before them, an or, an and, or they can be true and false. And to make it a little bit easier for myself, I didn't also define equality in the little language. I just used a function if I want to have two terms that are equal, and then it just outputs an formula that is equal to equality. So then you can have some equivalencies, like the rule I talked about in the beginning. If you have something and something, then certain things hold. So you can use these rules, you can apply them until you reach a fixed point, and then your input is normalized. So here you have De Morgan, that's the rule that pushes negation inwards. Distribution is to push ors inwards, and then you apply that until a fixed point, and then your input is in the right format. If you want to play with this, it's all on GitHub. So both the F# library and the C# code that generates the game, it is on GitHub. So, and they're separate, so you can use the library even though you're not interested in this particular game, but you want to do SAT solving on something else. So this is what it looks like in the interactive mode. I've defined a few variables, A, B, and C. And what I can do is I can say, well, I have a nice term here in somewhat of a human readable format, and if you don't think this is very human readable, wait until you see the real thing later. I would say this is somewhat human readable, and then here we have a make DMAX function. That is the input format that the SAT solver needs. You run it on a clause and you get the nice little input format. Here you have it. This is what the SAT solver wants to read. So then this certainly looks very, very human readable. They have a few funny conventions. Their variables can only be numbers. And negation of the numbers is a minus sign, and every line has to end with a 0 and a line break. Why? Why a 0 and a line break? I don't know, but this is how it works. This community has settled on that input format, so you can take my library and it will run it for you. This is what you get out then. So this is the assignment, and it goes on for 4,000 lines. This is what you get out if you write all the rules for the Quarto game. Lots and lots of lines of unreadable variables. This is really not something you want to type by hand. So now we can say the problem is solved. We have the right input format. We can feed it to the SAT solver. Eh? At this point, it's like maybe almost 9 or 10 in the evening. So is this going to work? So are you curious if it is satisfiable? I certainly was. Let's have a look at what happens. So you run it on your input file. Bam! That's it. Did you see how quick that was? It would have taken 90 hours to brute force, and it's just like, bam! You want to see it again? It's so cool. Can I go back? Yes. Pay attention. I mean, if you blink, you've missed it. There we go. Yes. Ta 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 ta. And this is no trickery. It's really that quick. It gives some statistics. So it has 4,000 clauses and 64 variables. So it's really, really, really quick. So that was like, yeah, we scienced that. Isn't that cool? You know, when do you get to use your CS degree? On a random day. So I said I was done, but of course we're not we're not really done yet. You get where this is going, because we've done this. We've transformed our problem to SAT. We've solved it in SAT, but we only have a solution in this world now. We still need to transform our problem back to the original world. We still have to make our binary form a decimal form. So what you can also do is run it with an input and an output file, and then your assignment is written to a file. So what you get then is this. So yes, it is satisfiable, and this is the assignment. Again, with the nice little convention of naming variables with numbers. And because the way that it works is not really important, but we get all our variables here. So now here we have to figure out the mapping back from the numbers to our original statement. And at that point, I didn't want to write any code anymore. I was like, what the heck? I'll do it on a piece of paper. I'll figure out what the mapping is. So here you see all the variables, and I circled all the truths to already visually get some idea if there wasn't a mistake. And here is the assignment. Isn't that nice? Look, it ends in a tie. Of course, now the obvious next question would be, how many of such boards are there? And do we take the mirroring into account and all sorts of transformations? But that's a problem for another day. So again, this code is on GitHub, both the F# library and the C# generator. So you can check it out. Now, of course, you think that is a lot of trouble to go through writing that whole library just for board games. Isn't that a bit outrageous? Oh yeah, well, that depends maybe. But there are also lots of real-life applications that SAT solving is really, really good for. So this is something that you might actually want to solve during business hours. Suppose you have two people and you need to divide them in groups. For instance, you need to make shifts in your company, or it also nicely generates to making a schedule. Some people work in the morning, they work in the afternoon. This is very easy to solve with an SAT solver. And even if there are some constraints, like B and A want to be in the same group, but B and C, they don't play together really nicely. If there are reasons that are constraints, this is really nice. So suppose, without loss of generality, we just want to have these 5 people, divide them in 2 groups. It's very easy with an SAT solving algorithm, because you can just say everyone gets a bit. Everyone gets 0 or 1, representing the group that they will be in. And then we can say, well, the bit of B should be the same as the bit of A, because they want to be together. But the bit of B and the bit of C should not be the same. And of course, if you want to make more groups, it's very easy. You can just give them binary code, so you give them 2 bits or 3 bits. You make these rules, you put them into an SAT solver, and bam, you get an assignment. And I know that this is a problem where there are people that wrote source code to try different options, but this is actually very, very easy, especially if you have a library that takes care of all the annoying DMAX stuff. And this easily generates to all sorts of forms of planning and scheduling. There are scientific papers, I kid you not, I'll tweet the link later, that use SAT solving to make basketball schedules optimal. So there are ways that are really, really useful that you can use an SAT solver other than board games. Another situation where you can easily use SAT solving is if you want to decide if 2 processes are the same. So suppose we have a specification process that says, it's called the minimum robot. You put in 2 variables and you get the minimum. So if you put in 0, 0, you get 0. If you put in 1 and 1, you get 1. We also have an implementation robot that says, okay, you give me an A and a B. If A is equal to B or B is false, then A, else B. Are these 2 things the same? It's not very easy to figure out if they're actually the same, if this is a good implementation for this specification. And this is also something you can solve with an SAT solver, because you can say for any given input, these 4 inputs, they need to result in the same value. And then here you have a truth table, and here you have a calculation. So you can easily generate these rules for. Typically, you do this on a finite set of inputs, because there are, of course, more complicated specifications where you could input anything you want. So you try it over a finite set of inputs, and then a solver can tell you whether or not it's equal. And this really nicely generalizes to hardware testing. Basically, it is already hardware testing and it's really used for that. But it's also used in other domains like biology, where they want to know if two DNA sequences are equal in some conditions, and that it's also used there. So that's it. That's everything I wanted to talk about. Before we go to questions, because I think we have some time for questions, I will summarize my entire talk in under a minute. So if you missed anything, if you came in late, if you're still like waking up from yesterday, this is your chance to still get the gist of it. And of course, if you were paying attention, this is optimal preparation for question asking. So I wanted to solve the board game of Quarto. Is it possible to end in a tie? You could do it brute force, but that is very, very slow. So instead, I chose to use an SAT solver to have somewhat more fun and also be done quicker. Although maybe it did cost me somewhat over 90 hours implementing, in the end, everything. So there are some tricks that make SAT solvers very, very smart, like unit resolution, quickly deciding on variables, and also keeping track of where you can apply this trick. So I wrote a little program, a C# program to generate the rules, and an F# library to make sure the input format is correct. This is what we got out of it. We ran it, and yes, Quarto can end in a tie. And there's not just for board games that SAT solving is useful. There are many real-life applications like hardware verification and scheduling that you could also nicely use SAT solvers for. That's it. Are there any questions? Yes.
So you started writing C# program.
Yes.
And then you made off and wrote an F# program for in retrospect, you should have written started with F# in the first place.
Well, actually, I'm not entirely sure. Because there are some things that are really nice in C# as well. Actually, it's a good setup to expressing my love for C# and F#. I really like the combination of C# and F# because in F# you do the things that are really functional. If you do the ugly like file processing or I'm not going to go back to the slides, but you have a number of nested loops. That's really C#. Looping over a few inputs. Of course, you could do it in F#, but having the data types, the pure manipulation in F# and doing the more like ugly stuff in C#, I sort of like that switching between pureness and non-pureness. I prefer that over something like Scala where everything is in the middle. Maybe it's just that my brain is very tiny, but I like to be forced to be in the functional world if I'm functional and do the rest somewhere else. But yeah, of course, you can do everything. I could have done it in Haskell if I really wanted to do functional only. But people that can do Haskell, they can also do everything themselves. Yes?
So that doesn't guarantee that the final state is a reachable state, right? Or is it like the Quarto rules that tells you that you can reach?
Oh, that's a nice one. We didn't do it, indeed, I didn't explain the rules maybe in enough detail for you to be able to decide that. The fact that that tie is there, that doesn't necessarily mean, that's a very good question, doesn't necessarily mean that this is something you can achieve. If the rules were so that maybe always you do three stones at the same time. But it's just every time you place a piece, so there's no rule that would prevent this from happening. And actually, it wasn't important for my talk, but the other nice trick about Quarto is you pick a piece, and then your opponent gets to place it. So that doesn't matter for the tie, but that is the only rule that is there. And other than that, it's just you place pieces on the board. So everything is reachable in theory. Maybe you would need a cooperative opponent to actually get it to happen, but it is possible. Yes?
So, your solution is very clear, nice. But would you consider using QDAO or GPU processing for brute force?
Yeah, so the solution is very clear and smart, but I could have also just done it on a few GPUs, and that would have also been quicker. Yes, but what's the fun in that? Then my talk would be 2 minutes. Look, I brute forced this. Here are a few machines. I mean, I could have done it on AWS if I would have wanted to spend €1,000 maybe. Then I would have been done in an hour as well. But that doesn't make for nice talks. Yeah.
Okay, let's say I propose
Yes. How much faster is the SAT solver than brute force? That really depends on your input, of course. If you want to prove that brute force is just as good, you can make very trickery. So if you have a situation where there's lots of conflicts, you have to backtrack a lot, then it gets very slow. But I think that the speed improvement I showed here is not. I didn't do any trickery to make it even quicker. So I would say it almost always pays off because they're so very good. And also, it sort of brings your problem to an even more generic space. So if you have it in this format, you can use an SAT solver, but there are also other type of solvers. I didn't talk about that, but there are also things called constraint solvers that you could also use in other similar but different problems. So having your problem in that space where there are solvers, you could benefit in different ways. And also this competition that I talked about is still ongoing. So you can also hardware gets faster and the SAT solvers get even smarter because every year there's still papers that add more of these tricks. So you benefit twice from waiting a little bit longer.
How would you translate the uncooperative partner to a problem statement that can be solved by the...
Oh, this is a good question. So how do you model an uncooperative partner? And there's a technique called alpha-beta pruning, and that is basically running an SAT solver every step of the game. So then you do the smartest thing your opponent can do, and then you have a move. And then again, on the other side, given that move, you do the smartest thing, and you repeat that for the whole game. So that's a little bit more simulation than model checking. It's basically a combination of the two where you model check on every step. That is how you can model someone that is really smart and that wants to do everything to prevent you from having a tie. So it would be similar, but then multiple times. Yes. So the question is if there is not a convenient or a normal solution, would an SAT solver still find it? So the nice thing is that the SAT solver doesn't know anything about the problem domain. It's just bits that it's manipulating. So either it will say it's unsatisfiable, or it will get an assignment, or in some cases it will just, if you have millions and millions of variables, it could just get stuck and not make any progress. But it's entirely independent of what you're modeling. So if there would be a situation, let's say there is a solution that no human could ever come up with. Let's say we're in that type of game. For the SAT solver, it's just, yes, P is true and Q is true and R is false. It doesn't know, it just gives you an option. So that is also nice. It's entirely independent. Oh, yes. Wait 90 hours? I mean, what can you do? But this is actually, it's a very nice question. It's almost like it's a setup, so this can be my final answer. This is why I initially wanted to give this talk, because this is a technique very few people know about unless they've seen it in university, and maybe they've seen it in university, but that doesn't necessarily mean you immediately understand to what type of practical applications you could use it. So you have to have a few of these techniques sort of in your briefcase of things you can use. And then if you see a problem, you can think, oh, maybe I could do here constraint solving or SAT solving or simulation. So by doing a few of these exercises, you can develop an intuition so I see this problem. Disclaimer, my entire master thesis was about SAT solving, so I see the problem. I see the Booleans. They jump at me, they say, please, SAT solve me. But that is something you can learn by looking at a lot of these problems and thinking, okay, here I could use simulation, or here I could use model checking, because this is of course a nicely polished story, but there are situations where an SAT solver would not be the good solution, because, yeah, as the person asked here in the second row, sometimes you have to also model the real world. You have to model an opponent that does some tricks, and then it's not a good solution. So yeah, if you don't know about these things, read some computer science books, but also practice. Try to not do maybe the thing that is most logical to you, because obviously the most logical thing here is just for E is a few nested if loops and then you're done. And develop an intuition for when there could be a better solution. Cool, thanks.